Welcome back. Today we're going to talk about section 4.3, the circular functions, and we need to do a little bit of investigation into angles to begin with and talk about where we've been with geometry, having angles that are acute or obtuse, just kind of sitting out there, and then we're going to start to talk about putting them in the coordinate plane and constructing our unit circle and things like that. Let's go. So here we go. If I've got an angle here and it has two sides, as angles typically do, and it's going to open up this way. We need to use some terminology here. So where it starts, so basically where the bottom would be on an angle in the coordinate or on an angle for like geometry in the plane is going to be the initial side. Okay, or at the very least, that's where we're going to start. So it's going to start there and open up, or open up negatively. And wherever it stops is going to be the terminal side. And so that's kind of where we can take our measurements from. How wide open is it? When we talk about trigonometry, though, we're going to start to put these things in the coordinate plane. In trigonometry, the initial side is always going to go on positive x. Okay, so the initial side is always going to be on the positive x-axis, and our angles are going to open up either counterclockwise. So if it opens up this way, this is a positive angle. So we're going to measure that in positive degrees. So this would be like positive 90 degrees, right? It would open up to a 90-degree angle. If it opens up down initially, okay, so this is going to be a negative angle. So like this would be negative 90. Now here's kind of the interesting part about this. Because this is positive 90, so if my angle opens up counterclockwise, this is positive 90, so this would be positive 180. And if I kept going with another 90, this would be positive 270. Well, you can kind of see why this becomes important, which way it opened up, because I could have an angle that opens up counterclockwise, it goes all the way around, and it's the terminal side is straight down, so that'd be positive 270. But if it had opened up clockwise, that would be a negative 90. And so as we go around, this would be negative 90, or I could call it, so this is negative 90 or 270. This would be negative 180 or positive 180, depending on which way I open. This would be positive 90 or negative 270. And there's everything in between here, okay? And so this brings us to our discussion of coterminal angles. So let's say, for example, I have an angle here, and it opened up this way, and what's going to become important is this arrow telling me which way it opened. This is a 45-degree angle. But I could also have an angle that opened up counterclockwise, and it stopped here, but in order to get there, I opened up clockwise and went all the way around, and then stopped here. Well, in that case, it's going to be 45 degrees plus a full revolution, which is equal to 405 degrees, okay? Coterminal angles are angles that share a terminal side. Okay, so do you see how this works? So if it opened up 45 degrees and then went all the way around again, it's at the same spot, so it's coterminal, together, terminal. The terminating sides, the terminal sides are together, like cooperation means together. Coterminal sides. Or what if it went all the way around again for another 360? So I could do plus 360 again and get 765, right? I could go around again. But also, let's consider that I had a 45-degree angle, but I didn't open up this way. I actually opened up this way, okay? And so if I do 45 minus 360, okay, I'd get a negative 315 degrees. Okay, so my angle here, this is a 45-degree angle above the positive x-axis, but I didn't open up that way. I went this way. I went counterclockwise, okay? And so when we start to talk about coterminal angles, an example of a question that they would give us is find and draw a positive and negative angle that are coterminal with the given angle. So for me, I like to visualize. Let's imagine we have a 30-degree angle here. It's maybe somewhat easier to visualize going this way. So I could have my positive angle would be 30 plus 360, which would be 390, right? My negative angle would be 30 minus 360, or negative 330. Okay, how could I count this? Well, let's imagine that I went this way. So it would be negative 90, negative 180, negative 270, and then negative 60, which would be negative 330, right? Well, how did I know I was going 60? This whole quadrant is 90 degrees, and I needed 30, so this part here would be, this is a little 60-degree angle here. So it's negative 90, negative 180, negative 270 plus 60, okay? So mathematically, maybe it makes sense to you more mathematically. For me, I'm a visual learner. The math makes sense, but I like the picture. It's important to get that first angle in there. So negative 150, where's that going to be? Well, if this is negative 90 down here, and this is negative 180, I've got to go negative 90 and then another 60 degrees. So negative 150 would be about right here. Important, very important to put that arrow, right? And so this, to do a positive angle, would be negative 150 plus 360. Which would be equal to 160. Okay, and then my negative angle, I could do negative 150 minus 360, which would be equal to negative 510. Okay, so I can continue to go around and around and around and try to get, that's not right. You guys are probably like, what the heck is going on here? This would be equal to 210. Okay, and so you're probably thinking, well, how does this work? Is there any end to it? What, like, could I subtract another 360? Yeah, there's an infinity of coterminal angles here that are going to allow us to find an infinity of angles. Now, I'm probably going to ask you to do one positive, one negative, but that's kind of our basic gist. All right, so let's think about this for a second. 2 pi over 3 radians. Now, if you're familiar with the unit circle, you probably maybe might remember this. But if you're not familiar right now, we can do a little bit of pre-work on this and talk about converting, right? So 2 pi over 3 radians, if I convert this to degrees, and remember I want what I want on top, so 180 is on top, so I can do, the pi's are going to reduce out. So I've got 360 over 3, which is 120 degrees. Okay, and so this would be 90, this is 180. So if I go 90 degrees, then I go 30 more. So here's 120 right here, or 2 pi over 3. They are the same thing. And so to get a positive angle, I'd go 120 plus 360, which would be 480. A negative angle would be equal to 120 minus 360, which would give me negative 240. Okay, that's actually not the answer, okay? Because the answer is got to be in radians. So you have two choices. I can convert these to radians, or I can think about this in terms of pi. Let's say, for example, I had 2 pi over 3. Instead of adding 360 degrees, I got to add 1 revolution. So I could add 2 pi to this. Okay, so that would be 2 pi over 3 plus 6 pi over 3, which would be 8 pi over 3. There's my positive angle. I could also do 2 pi over 3 minus 6 pi over 3, which would be negative 4 pi over 3. Okay, and so I either add and subtract 360, or I can add or subtract 2 pi. Okay? All right, I'm going to do one of these, then I want you to do try the next two. The next thing that we're going to do is this. So we just put some angles in standard position. We use the angles. Sometimes they're going to give us the sides. Okay, and so they're going to give us the sides, and the sides are going to look like this. Let theta be an acute angle in standard position whose terminal side contains the point 5,3. So think about that 5,3. 5,3 is in quadrant 1. And this is the x and this is the y. And so I've got a terminal side in quadrant 1, and this forms a triangle here. Check it out. And we're always going to go to the x-axis, and my x and y are going to be determined by this point here. So my x is 5, so this side length is 5, and this side length is 3. Okay. Find the 6 trig functions of theta. Well, theta is the acute angle in standard position, so this is my theta. My theta is always going to be in the middle. And here's a little side note here. These are what I like to call the Bowtie angles. So we're always going to have problems like this, and you're always going to make the triangles to the positive x-axis, or to the x-axis, sorry. And so your 90-degree angle is always going to be there, and here are your possible thetas. And check it out, it looks like a little bow tie. That's why I call them the Bowtie angles. Okay? And so with those bow tie angles, anytime they say, let theta be an angle in standard position with a terminal side that contains the point da-da-da. Okay, you're going to do one here with -5, -3, and -4, -6. It doesn't matter. You're always going to draw your perpendicular lines down to the x-axis, and you're going to use that to make yourself we're going to call them reference triangles. That's what they're called, reference triangles. And then we're going to find the 6 trig ratios from there. And so when we look at this example, once I put it in standard position and I outline where my x and my y are, x being my horizontal component, y being my vertical component, I can find anything, any of the trig ratios that I want. They want all 6 of them. Here we go. The sine of theta is the opposite over the hypotenuse. And so I've got 3 over my hypotenuse. Now how do I deal with my hypotenuse? Well, since this is a right triangle, I'm going to go 3 squared plus 5 squared is equal to my hypotenuse squared. And my hypotenuse in these is always going to be equal to r, because it's going to end up being the radius of the circle, okay, when we do the unit circle. And so I've got 9 plus 25 is equal to r squared. And r is going to be the square root of 34. Okay, I do this example to also show you 2 things. R is the hypotenuse. R is always positive. Okay, R is always positive. So it could be plus or minus square root of 34, but it's because it's the hypotenuse, it's always going to be positive. And as you can see, my x and my y aren't always going to be positive. Like if it was down here, if my y component was down here, it'd be -3, or if my x component was over here, it'd be -5. R is always positive. Okay, and so what I like to do is, we see very quickly that we need all 3 sides to do the 6 ratios. So I like to do this: x equals 5, y equals 3, r equals root 34. And then when I do my cosine of theta is adjacent over hypotenuse, 5 over root 34. Tangent of theta is equal to 3 over 5. When I do my other 3, I'm going to go cosecant theta is equal to root 34 over 3. Secant theta is equal to root 34 over 5. They're all the reciprocals. Cotangent of theta is equal to 5 over 3. That's all 6 of them. Put it in standard position, find all 3 sides, lay out according to the ratios that I already know about from a previous lesson. Okay, so that's all there is to it. I'd like for you to try this one. Okay, try this next one. Notice what's different about it. So in this case, our ratios, I'm going to put my bow tie angles. So if I've got -5, 3, I go -5 up 3. So this is my angle. Draw my triangle to my x-axis. So this is -5. This is 3. Okay. lay out my x, lay out my y, lay out my r, and then find your 6 ratios. Pause here, try it, come back, and I'll do it for you. All right, so my x is -5, my y is 3. Like this previous example, it's going to be root 34. What does that change? Well, check it out. Here's my theta. The sine of theta is equal to the opposite. And remember, my radius, so my hypotenuse is always going to be a positive value. Sine of theta is opposite over hypotenuse, so 3 over root 34. Notice, it's the same as up here. Even though my triangles is in my second quadrant, my cosine changes though. It's going to be -5 over root 34. My tangent of theta is my opposite over adjacent. So it's going to be -3/5. Now notice, the whole ratio is negative. The 3 isn't negative, but because I'm dividing a positive by a negative, it becomes a negative. So my cosecant is still root 34 over 3. My secant is negative root 34 over 5. And my cotangent is equal to -5/3. Okay? Same thing happens when I've got two negatives. It's just going to be in the third quadrant. So that's something that we can do. Okay, now, we've done this now a couple of times. We can put things in standard position. I want to look at something that is going to help us translate into talking about the unit circle. Okay? Let's look at the 6 trig functions for 315 degrees. This may not seem like the same question to you. But here's what we're going to do. I'm going to draw this angle in. Okay? I want to draw it in. And then we're going to see exactly how this works. And so we're going to put this angle in standard position. So 315 is going to be, so if this is 90, and this is positive, so we're opening up counterclockwise. So 90, 180, 270, plus another 45 here. And remember, when we're drawing this using a reference triangle, the reference triangle, those are going to be those bow tie triangles, right? And so I'm going to draw my triangle up to the x-axis like this. Okay, so don't draw it over to the y-axis. That would be incorrect. And so essentially, I need to calculate what this angle is here, and this is 45 because it's complementary with this one. So what are my values? So if I'm trying to find the 6 trig functions, up top, they were giving us numbers. Well, here we actually do have numbers. We have the smallest ratios that still make a 45, 45, 90 degree right triangle. So for 45, 45, 90, this is going to be 1, this is going to be 1, and let me get this 45 out of the way here. Got to do a little redraw here. This is going to be square root 2. How do I know that? Well, remember, in a 45, 45, 90 degree right triangle, the two legs are x, and the long side, the hypotenuse, is x times root 2. Well, I'm just going to make x 1. And so all the ratios are the same. So then I've got 1, 1, square root of 2. Because I'm in the fourth quadrant, I've got to make this -1 because it's below the x-axis. That's the trick here. When I lay out my values, x is equal to 1, y is equal to -1, and my r, which is never positive, is square root of 2. So now when I find the 6 trig functions, the sine of theta is opposite over hypotenuse, so -1 over square root 2. And I can rationalize that. Equals -root 2 over 2. The cosine of theta is adjacent over hypotenuse. 1 over root 2, which gives me root 2 over 2. Tangent of theta, opposite over adjacent, -1. So my cosecant of theta is the reciprocal. So it's -root 2 over 1, which is -root 2. I don't know what that is. Secant of theta, sometimes I'm just crazy, I'm just drawing. Okay? And this is root 2 over 1, which is root 2. And this is cotangent of theta, which is -1, because the reciprocal of -1 is -1. All right, and so now we can find a bunch of different angles, a bunch of different trig ratios for a bunch of different triangles without using a calculator, because using coterminal angles and reference triangles, I can draw these in. So if I go to find the cosine of 120, that's not a 30, 60, 90, and it's not a 45, 45, 90, but if I draw it in, what I'm going to find is that if my 90 degrees is up here, and I go 30 degrees farther, this is my 120, I can draw in a reference triangle. What's my angle here? Well, if this is 90, then this is 30, then that must mean that this is 60 here. So now I have a 30, 60, 90 degree right triangle. How does that play out? Well, this is 1, but it's -1 because it's in the second quadrant. This is √3, and this hypotenuse is 2. Okay? And so I can find the cosine of 120 because the reference angle is 60, meaning it forms a 60-degree angle with my x-axis. My reference triangle is right there. And so the cosine is adjacent over hypotenuse, -1/2. Done, no calculator needed. I can verify on my calculator. Tangent of 300. 1. Draw in standard position. 2. Use reference triangle. So the tangent of 300, 90, 180, 270, 270 and another 30 would be this one here. Goes to the x-axis. And so my angle here, this part is 30, so this is 60. Which means that this one's 30 down here. So this is 1, this is -√3, and this is 2. So now the tangent is opposite over adjacent, -√3 over 1, which is -√3. Secant of pi over 3. The secant of pi over 3, and feel free to pause this, and when you come back I'm going to explain it. But when we start to do complicated ones using radians and functions that aren't on the calculator, we have to remember our principles. Draw in standard position. Pi over 3, where is that? Well, pi over 3 is 60 degrees. Okay, so 60 degrees is right here, which means that this would be 30. And if this is 30, then this is 1, this is √3, and this is 2. Secant is, so if secant goes with cosine, and cosine theta is adjacent over hypotenuse, then this is hypotenuse over adjacent, so that means it would be 2 over 1, which is 2. Okay? That's all there is to it, guys. Draw that thing in standard position. Whether you've got a number, you got numbers, meaning an x and a y, and you lay out the triangle based on its side lengths, or you've got the angle and you use reference triangles to put it in standard position and then draw a reference triangle to that x-axis, you've got everything you need to draw that picture and find those ratios. Okay? Thanks for watching, and we'll see you next time.